Welcome to qnawire.
For a given problem, for part A, we use the information from table 42.2. We can find the energy gap for CdS to be Eg is equal to 2.42 electron volt. So any photon from Balmer series with energy greater than Eg will be observed. The wavelength associated with this energy will be lambda is equal to Hc divided by E, which is the product of Hc is 1240 electron volt nanometer. This divided by 2.42 electron volt, this gives us 512 nanometer. So the wavelength associated with this energy is 512 nanometer. Since the energy is inversely proportional to the wavelength, then if we take the photon with energy greater than Eg, then we must take the wavelength shorter than lambda. Balmer series lie between the shortest reduced by the transition of n is equal to infinity to 2, which has the energy of delta E is equal to constant, which is a 13.6 electron volt divided by 1 over 2 square minus 1 over infinity, which gives us a 3.4 electron volt. The wavelength corresponds to this energy using the equation that we wrote earlier. Is lambda is 365 nanometer, and the longest produced by the transition n is equal to 3 to 2, which has the energy of delta E, that is 13.6 electron volt, 1 over 2 square minus 1 over 3 square is equal to 1.89. The wavelength associated with this energy will be then using the same procedure that we did earlier, Hc divided by energy, which gives us 656 nanometer. The next transition is n is equal to 4 to 2, which has the energy delta E of 13.6, 1 divided by 2 square minus 1 over 4 square, which gives us 2.55 electron volts. Then using the same equation that we did earlier, we find the lambda, and the lambda we get here is a 486 nanometer. From these calculations, we see that all the hydrogen Balmer lines, except for the lead line, at 656 nanometer, will be observed by the CdS crystal. For part B of the problem, the transmitting spectral line is the red line at a wavelength of 656 nanometer, since it is not observed.